I emphasized all right. So in the last class on Monday, I showed you this particular table here, which is in the textbook actually. And you're going to see that we have those regions of the electromagnetic radiation and the kind of light that we use and what we use it for in the analysis. This is what this table is saying. For example, radio waves, where it is used, and the approximate range in meters. You can convert meters to either a wave number or nanometers, or that kind of thing. Remember, you can use the formula. Energy equals to h nu, right? E equals to h nu. And h is Planck's constant. That is a constant. So if you know the energy, for example, if you say the energy E, right, is equal to, you're given the energy, then you can find the frequency nu, h nu, okay? So in this case, you can see here the various radio waves, shortwave radio, AM radio, FM radio, and then the television bands, those channels there. But you can go to the microwaves and what they are used for. For example, microwave energy, or the microwave portion of the electromagnetic spectrum, is used to probe the rotations of molecules. You can see here, it's used to probe rotational motion of molecules and in microwave ovens. So usually that's what we use it for. If a molecule is rotating and we want to see its rotational spectroscopy, if it rotates, it's going to give you some spectra. So this is, you might not realize what rotational spectroscopy is, but it's diagnostic of a molecule. Then you go to infrared. I emphasized infrared light. So last time from meters there, 10 to the minus 4 meters to 7 times 10 to the minus 7. So we can use it, we use it very often. In technology, for example, they use it in fighter jets actually, okay? So you might know that that's what is used in infrared light. It's used to probe the vibrational motions of molecules, and you can sense molecules from far. And you have the visible light. You can see the visible light, which we see, and you can actually notice 7 times 10 to the minus 7, they're about all the way to 4 times 10 to the minus 7. And you can actually change those meters to nanometers, right? You can change those to nanometers. For example, a very quick 7 times 10 to the minus 7 all the way to 4 times 10 to the minus 7. That's orders of magnitude of about 3 orders of magnitude, about 1,000 range. So roughly in the visible light, you all know this right away. If it is from around 400 nanometers to 800 nanometers on the ballpark. So that's what we are talking about, the nanometers, what we can see. And then UV, you can see all the way from around, UV actually can go down to 180, and molecules such as the nonmetals, for example, tend to show some ultraviolet spectrum. For example, you cannot analyze sulfur using the UV light. No, the visible light. Okay? But you can analyze sulfur using the UV light. And the reason, and normally when you analyze these elements, sulfur, for example, the nonmetals, you have to do the analysis in a vacuum, right? Which means normally it's below 190 nanometers, okay? So that's what we are saying here. The ultraviolet light, it causes sunburn, it kills bacteria and so forth. X-rays, you can see that, and cosmic rays. my goal in showing you this is just to make us be aware that every section of the electromagnetic spectrum is useful, every portion of it, and we use it in spectroscopy. Here is something that we have talked about from our last class. What are the facts of light? When we talk about light, in this case, we are not talking like laymen in the streets, all right? We're talking about the whole spectrum. So one of the equations that we know, the speed of light in a vacuum, speed of light, C, is going to be equal to nu times lambda. So remember last time I tend to remind myself what speed is all about, right? Speed is whatever length over what? Over time. 1/time per second is the frequency, right? That is the mu. Lambda is distance, lambda. So from that kind of analogy, I find it very easy for me to remember the formula. Speed from the basic definition, length over time. So length is lambda, wavelength, times 1/per second. That's frequency. So we have this. Light is equal, the speed of light in a vacuum is 3 times 10 to the 8 meters per second. So that is the basic formula that we normally are going to use. And the energy of a photon, as you see, you don't have to remember that number, all right, the Planck's constant, but the energy of a photon, E equals h nu. H is Planck's constant. I usually give it in the test. For example, in today's test, I give you the constants. Right? I will normally give you the constants. And then whatever you do with them, you use them or not, that will be up to you. So I usually will give you the constants. So Planck's constant is 6.62608 times 10 to the minus 34 joules second. Joule second. So you can see there, joule second, right? H nu. This here is nu. And frequency there is 1/second, correct? So you can see 1/second. So using the formula there, so you see it is E equals to H nu, everybody can see. So which means Planck's constant, 6.626. This is well known to, you can see 5th or 6th decimal point there, 0.8 times 10 to the minus 34 joule second times nu is 1/second. So you can see the second cancels out, then you get your energy in joules. All right. So joule second is the Planck's constant. So you can E equals to h nu, and therefore you can now we know this formula again from the last class, right? Remember, we know this formula, and so E equals to h nu, and we have already said from this formula where C equals to lambda, so we can replace the frequency here. So knowing that C equals to, so which means that nu equals to C over lambda. So you can replace it in the formula. You can replace it here. And if you replace it in the formula, so with that rearrangement, so you can see if the frequency is the frequency C over mu, that's in hertz, then therefore you can derive the formula, you can replace it in E equals h nu and replace the nu. So E, the energy of a photon is equal to nu, that is C, E equals H nu. So we want to replace that. So this becomes HC over lambda, correct? So that's just a simple derivation from the two formulas. And you have actually in the homework from chapter number 6, you have these simple problems to enable you practice. So I urge you to look at them. Although I may not test you on this today, I will test you in the second exam. Okay. Yes, sir.
So these equations won't be on the exam today?
No, not for today. What I will test you is some interconversions. If you have used them, fine. But I will not go extensively into some conversions. Okay?
What do you mean by interconversion?
Remember last class, we talked about how do you change nanometers to wave number. That's what I mean. Okay. In other words, here is Marion, here is it stems from this electromagnetic radiation, right? So for example, in this electromagnetic radiation, you have, that is nanometers, that is frequency. So you need to know how to convert wavelength to frequencies in hertz per second. You're going to use the formula E equals H. Yes.
So we only need to know how to transfer from those two.
That you need to know. Yeah, I can't say you only need to, but that you need to know. All right. Okay. And so that's what we have said there. And this is just a derivation. This formula here, I don't want to go into the derivation. It's simply, notice, this is just calculus, okay? Basically, it's calculus. Using a formula, you take the derivative of one side and the derivative of the other, and then substitute, okay? But I won't go into that. All right, again, this is what we already know. For example, now this is, in this particular table here, notice again, we are going to that electromagnetic radiation, that particular figure. And with each one of them, for example, we have the usual wavelength range in angstroms, and we have others in nanometers, microns, and then there is a conversion from the angstroms or nanometers to per second. I gave you a challenge last time. Remember the UV range or the infrared range in terms of nanometers. What was the range again? Look it up. The infrared. What range was it? Infrared. So two numbers. What was the range? Actually, it's up here. Yes, it's up here. Yes. It's 0.78. What? What are the units? Microns, all the way to 300 microns, micrometer. So how do you convert? I emphasize this because we're going to face it. How do you change 0.78? Okay, 0.78 microns. How do you change it to per centimeter? All right. So in other words, how do you convert 0.78 to correspond? Notice here, if it is microns, you are saying that is 0.78 microns. So in that case, microns, we are reminded on what micron is, right? Micron is, this is 7.8 times 10 to the minus what? So now we have converted it to a meter, all right? And we want now, remember this is energy, right? So how do you now convert this number here to per centimeter? Or inverse centimeter, rather, inverse centimeter.
We gotta get into centimeters first.
Okay, so how do you do that? So let me write it here on top again. 0.78 times 10 to the minus 6 of a meter. Now tell me what to do. So we want to change it to centimeters first, right? So 1 meter as 100 centimeters, right? So just simple conversion without knowing the formula there. And so after that, what do you get? You get a number, right? So you get 0.78 times 10 to the minus 4, correct? 0.78 times 10 to the minus 4. All right, so once you get to the 10.78 times 10 to the minus 4, 0.78 times 10 to the minus 4 of centimeters. Remember, we want to convert it to per centimeter. There is one critical step. You can do the math and you can get it, but what does it turn out to be? You do 1 over 0.78 times 10 to the minus 4 centimeters, then what do you get? Yes, just that's from simple math, right? So you get that. Get that, right? And then this other one, you take 300 microns, you do the same way, and you get that. Does that make sense, class? So you inverse 1 over that once you convert 300. So this also, notice what this is telling you. 10 to the 4th is around 10,000, right? 10,000, this is 13,000. So per centimeter, this, I'm emphasizing this, because we need to know this. So now you see we are in the range of 13,000 to around 33 wave numbers. So really the infrared and Raman, when we do measurements, is in that range. Normally in that range, that's where we measure it. There is actually far infrared, which can go to 20,000 wave numbers. So you can see that interconversions, you only need to take care of the units and make that conversion. Anybody here would, I don't hope anybody would have such a problem, all right? So you can see. So we use infrared absorption and Raman scattering for rotational and vibration of molecules. The rotation and vibration of molecules. That's what we use it for. And you can see down here on this corner here, which some of you may not see, that corner there gives you some interconversions, right? So, so that everybody knows how to do it. Does anyone have any question here? All right. So the key point for our information, I've just given you the value for the infrared from this table. If you use, for example, electron spin resonance, that is called ESR, which is very close to the nuclear magnetic resonance, but we use the spin. That also is useful for the spin of electrons in a magnetic field. So you're measuring how electrons are spinning in a magnetic field. Now you go to the NMR that we have here. So you notice electron resonance, electron spin magnetic resonance, that's for electron. You're probing electrons whenever they are in an atom or a molecule. And then when you go to NMR, nuclear magnetic resonance, in the medical field, they call it what? MRI, because by its historical, because people fear, if we call them nuclear is not so good. It is, okay, they say, let's call it MRI. but the two work on the same principles actually. If you know the history of how people killed the nucleus when they bombarded it in 1945 around there. So they call it, so they have, notice here, the spin of electrons in a magnetic field. When you talk about NMR, the spin of the nuclei, so we notice electron spin and nucleus spin. So here is the spin of the nucleus when it's placed in a magnetic field. Really, that's what we are doing here. You have a nucleus with its surrounding environment, that is, and you probe the proton spectra or carbon or otherwise. So any other question as far as this is concerned? Everybody knows, Marion, this is what I was talking about. Okay. 80. Last name, why? No, the reason is, I think I know a friend's daughter called Marion. So I think probably that's why. So. All right. Now, here is the basic, the other thing I want to talk about here, the physics. I will go through this very quickly so that each one of us knows these terms. These are the terms you have to look up and answer the questions. Okay. So what happens to electromagnetic radiation when it interacts with matter or when it interacts with an analyte? What happens? So there are several things that happen. So here are the properties that we make use of in analysis. When we talk about diffraction, what is there? I need everybody to know what this table is talking, or this slide is talking about. These are some of the properties that we probe. We use diffraction. You would have to look up diffraction and tell me what diffraction is. I'm forcing you to understand that. Okay. And then we have transmission. Okay, the transmission of light, the diffraction of light happens. We have the refraction of light happens. We have the reflection of light. There is refraction and there is reflection. What's the difference? Light is refracted and light is reflected. So what's the difference between the two? What's refracted refraction?
Refracted light is light waves that are bent through an object.
That's the key.
Reflected is bounced off.
Yes. So it bends when it comes through either a barrier, right, of different indices, reflective indices. We talk about refractive indices. So bending of light, reflection, and bouncing off is reflection. And then there is scattering. The scattering of light is used either in Raman spectroscopy. You can see that we talk about these things. You may not know all the details, but each of these effects are used in analysis actually. Every instrument that we use in spectroscopy or when we do measurements is usually uses one of these properties. It's light diffracted, is diffraction of light. And you talk about the what do you call the index? No. We talk about the diffraction of light. Like for example, X-ray, XRD. XRD stands for X-ray what? Diffraction. We use that. So transmission, we talk about TEM, SEM, or even absorbance. What is SEM? Scanning electron what? Microscopy, which we use in imaging surfaces. You can see atoms and the arrangement at the atomic level, or the aggregation of the analyte atoms. All right, and you can zoom in, or TM, transmission electron microscopy. You can talk about refraction. You can talk about reflection and scattering of light. We use it in Raman scattering. And so here are some key words. Now, I need us to concentrate on this last diagram here, the last one on the bottom here. You see power in. P naught, all right, the power in, the intensity of the instant radiation, power in, power sub naught. Then you have the P, sometimes it's P sub T, right? Although it's not shown here, P sub T. So if the light, the electromagnetic radiation interacts with the sample is in a container, the analyte is in the container. You can see here in the green diagram here, or this figure, that is representing a container with a sample. And notice there, it has a distance that that light travels through. That is B, right? The length through which the light travels when that light interacts with the analyte is B. That's what we call the path length, right? The path length, B. Or sometimes we call it L. So you can see when it interacts, notice we have the power, the intensity power, given per angle. So notice this particular formula, you can all see transmission. Transmission is the power that comes out, the transmitted light, over the incident light. That's a very simple formula, transmission. And if you convert it to a percentage, what do? Multiply by 100, which becomes percent T, right? You have this formula, it's actually in the textbook. Percent T, those are the problems I've assigned. Percent T equals to power in over, no, the transmitted power over the power in times 100% T, all right? So that is going to give us this formula here. So notice, if you take the inverse, the absorbance, this is now Beer's law. Absorbance equals to log, notice here, what is this? How is this related to T? It's the inverse, so 1 over T, right? So 1 over T, T to the, so you notice this is T, but here absorbance equals to, if I write on this, absorbance is equal to log 1 over T. So in the math, that is equal to log, T 2 minus 1, right? And you know by the laws of logarithms, you take that inverse to the outside, right? So that becomes A is equal to minus log T. Does that make sense there? So this is what you have in this formula. And that is the formula that we normally use. A equals to minus log T. And you know what transmission. You are comparing the light before it interacted with your analyte and the light after. That's the ratio. So remember, if I remember, some of you were asking me in the, when I gave you the first lab, what is this percent T? So that's that ratio. So in the infrared spectrum now, you can remember in that first experiment, it's percent T, right? So you can see now the relationship between percent T and absorbance. Are we together there? So in real terms, when you acquire an infrared spectrum or a UV light spectrum, you can also calculate T transmission. So in the case of the first experiment that I gave you, where you had to deal with the y-axis being in percent T, it is actually giving you this percent T, or if you want to convert it to absorbance, then you have to say A equals minus log T. We together there. Okay. Now this is important. So we have properties of the electromagnetic radiation. I need to do a problem here, although it's going to come later. And you know, there is something I want to say here. I would mention it later. And I ask this question and people forget. I say, if the absorbance of well, the analyte at a given wavelength, let's say, I'm going to make up a number, right? If the absorbance, this is an analyte, it has its UV spectrum. If the absorbance of that analyte at lambda equals to 200 nanometers is a given number, all right? Are we together there? I've given you the absorbance of the analyte. I've given you the wavelength, which means you have to measure the absorbance at a given what? Given wavelength. And then I will then give you a number. Later on, I turn around and ask you what will be the absorbance at a wavelength of, remember I gave you 300, right? What will be the absorbance at 450 nanometers? You know what people start to do? They take their pens and start doing the calculation. The point I'm trying to convey, and I would bring that question, is you need to know that the absorbance is wavelength specific. You can't tell. Don't put your brain into pen and paper. Well, I'm just, I'm giving some insightful thing that you need to pay attention to. If you measure the wavelength, or if you measure the absorbance at a given wavelength, that absorbance, like those of you who are going to do the UV, right? That absorbance, you measure it at a given wavelength, okay? That absorbance will be different if you measure it at a given wavelength. You have to stick to that wavelength before you can calculate. So the question, here's the question, I think I wasn't very clear. So the absorbance at a given wavelength is number A equals minus log T, all right? And we know what A equals to epsilon CL or B, all right? So what I say is, this is the absorbance at a given wavelength is going to be, so that is the concentration. So I put that lambda there, you're seeing that? So you can calculate, and then I will give you either the concentration and the path length, that is B, and then ask you to calculate mole absorptivity. Now, and then I come back, I say, this is maybe absorbance at 270, okay? So what will be the mole absorptivity at 280? You see there? So you plug it in. Can you do that? No, you cannot do that. You have to know. You have to know the absorbance first. I will bring that question up. I'll bring that question up for clarity later. I'm just going ahead of myself. So what happens to electromagnetic radiation? We all know that. What are the properties of the electromagnetic radiation? I've emphasized some of the things that happen. One, you can have these effects with properties of electromagnetic radiation. Remember, light can be as a wave. And so you can have the superposition of light or of waves. Waves can be superposed on each other. You can have diffraction. You can have coherent radiation. You can have transmission, dispersion, refraction, reflection, scattering, and the polarization. I only mentioned a few. I've put in others, as you can see there. So these are some of the effects. And as I've said, in the homework, I am forcing you to know these particular ones, even once or twice in your life. I would like people to know how to define those. Okay, let's deal with each one of them now. What is diffraction? You notice there, this is light treated as a wave. So it comes to, okay, it comes to an opening, and you do this in the physics, for example. And then that light, notice it's going through that aperture, and it can change direction. You're seeing that? It can change direction, it can be diffracted. So diffraction is the process whereby this is a parallel beam of light is bent as it passes a sharp barrier or through a narrow opening. So it gets bent, it's no longer parallel. So that's the definition of diffraction. Bending as it comes through a barrier. And this usually would happen. Diffraction can occur, for example, if it changes from one medium to another medium of different reflective indices. Now let's deal with transmission. We used transmission. What was the formula again? T equals P over P naught, all right? And what's the relationship between absorbance and transmission? Minus log of T. A equals minus log of T. Those two basic formulas are important. And we are going to add another one using BS law, all right? So in transmission, the rate at which radiation propagates through a transparent medium is less than in a vacuum, okay? In a vacuum, that's where we have the speed of light measured in a vacuum. What's the number again for the speed of light in a vacuum? 3.0 times 10 to the 8. What are the units? Meters per second, all right? So that number is a measurement done in a vacuum. If you change that from a vacuum to air, then it's no longer 3.0. So we are saying here the rate at which radiation propagates through a transparent medium is less than in a vacuum. For example, it's going to be 2.98 or less than 3.0. And it depends on the kinds and the concentrations of the atoms, the ions, and the molecules making up that medium. So we talk about the reflective index of the medium. So reflective index, as you can see here, this symbol, Greek symbol, what do you call that symbol? You call it neta or something? Okay, that is a specific, it is written as that. That is the reflective index in a given medium of any object is equal to C over the frequency within that particular medium. And usually, transmission, you can go stepwise, the process of transmission involves polarized atoms, ions, or molecules. So this is the reflective index. If light is transmitted from one particular medium to another, then you need to know the reflective index of that particular barrier or that particular barrier. Okay, so we have defined the two terms, diffraction. The other term we have defined is what? Transmission, a very simplistic manner without going into the equations. And then we want to define refraction. Do you recognize this law here? What do you call that law? Yes, that is Snell's law. Snell's law on refraction. So when radiation passes at an angle through the interface between two transparent media, So you can see here, this is theta 1, and it's going through two transparent media with different optical densities. What's the other name for optical density? Well, each of that object will have different optical densities, but it's also absorbances. So it's also going to have different refractive indexes. So because of that, then you have an abrupt change in the direction because they are not the same. They don't have the same refractive index. So you can see that theta 1, you put a normal to the instant light, put a normal, that normal to the instant light. And then you can see now, it is now bent when it goes through the other medium. And you can see theta 2. So the medium 1, M1, going through medium 2 of different reflective indices. So you have, if you put the normal to the surfaces, and then you have the two angles, theta 1 and theta 2, then you are going to have sine theta 1 over sine theta 2 equals to N2, notice the way it is the N2 over N1, the refractive index of 2 over the refractive index of 1. And then that's going to be equal to, remember the previous formula, this one here, see there? So the light is common, the speed is common. So you put those into the formula and you notice N2 equals to mu2 over mu1. That's Snell's law of refraction. Snell's law of refraction. Sine I or sine I over whatever the sine. So we are talking about in terms of the angles, right? This Snell's law dealing with the angles. Refraction, the bending of light when the light goes through media of different refractive indices. The light is bent. Now let's talk about reflection. I think you can see here, we have already defined what reflection is. We have talked about it in our class. And notice reflection. What did you use? Bounce back? Bouncing back at an angle? All right. I'm just taking Mr. What's his name? Your name?
Robert.
I'm using your words. Okay. So Michael is the gentleman. Okay. So you can see here the incident radiation. You can see the incident radiation to the surface. We have two media like the previous one. The incident radiation to the surface is going to be bounced back, it's going to be reflected. And again, you can see the reflected, the incident reflection, the IR of I naught. What is I again? What is I? The what?
You're saying the light beam that's reflecting, like after the reflection.
So after the reflection, so R is reflection. O is before.
Yeah.
That is the light, right? Over IR over I naught, the intensity of that reflection is going to be equal to the difference between first, the two indices, reflective indices squared over the sum of the reflective indices of the surfaces. Okay. And now we go to the other one here, what we call scattering. Scattering is used in Raman spectroscopy. We use it in Raman spectroscopy. Each of these properties of light is used for a specific purpose. Okay. So I want to stop here and say I'll pick up on Raman spectroscopy. But there is something I want to emphasize in this chapter on Friday. You sure want to miss on that because I would emphasize on the Jablonski diagram on Friday. And then I'll come back to emphasize it again. So make sure you don't miss that lecture on Friday. All right, I'll see you tonight. If you want to come and do your homework, you can.